In the last discussion, we looked at Hooke's law and the force on a spring and solved the problem numerically. In today's discussion, I'd like to solve this problem analytically. It's one of the problems that can be done analytically, and so it has some very interesting mathematics and stuff that you'll use over and over again, so I think it's worth going through it. It's going to be new for many of you, and I realize that. So just reiterating from the last time, the force law for a spring says that we have a force which is proportional and in the opposite direction from a displacement. It's minus the spring constant times delta x, the extension or compression of the spring. So here is the diagram we used in the last class. We have a mass sitting at equilibrium on a frictionless surface. We displace it to the right by some amount delta x. It's going to experience a force in the opposite direction, and the magnitude of the force will be given by the spring constant times this displacement delta L. So writing Newton's equations for this lateral motion says that the change of momentum with respect to time, that's the force, is equal to the spring force minus k delta x. All right? We're going to combine this now with the expression from calculus, which says that the time rate of change of position is equal to the velocity. And using the fact that the momentum is equal to the mass times the velocity, now I'm going to change this momentum and write this as mv up here. V is equal to dx dt, and so this term is going to turn into the second derivative of the position with respect to time. That's what this is coming from. And then I'm going to have the force. So now what I have is a single second order differential equation. The momentum does not appear in this equation at all. We only have the position, x. So it has a single variable, but it is a second order differential equation. So the last time numerically we solved a coupled set of first order differential equations. In this case, we're going to solve one second order differential equation. And if we happen to need the momentum, we'll get it by taking the derivative of the position, multiplying times the mass, and we'll get the momentum. So, using some math jargon, this is a linear second order inhomogeneous differential equation with constant coefficients. And it's a solution that you can find. All right? So let's go through these terms just so you know. You'll hear about them in math. It's linear in that x is always appearing to the first power. You never see an x squared here. It's second order because the time derivative is occurring to the second power. So it's a second derivative. It's an inhomogeneous differential equation because it has a term that's a constant. The one term, this term has an x, this term has an x, but k over m L0 is a constant. That makes it an inhomogeneous differential equation. And it has a harmonic solution, but I'm going to show you that in a bit. So this is a slightly different problem than we solved yesterday, simply because it's more amenable to being solved analytically. We ought to get the same answer, but we'll be doing it a very different way. Now, one more thing I want you to see about this problem is I don't have any vector signs on this equation. So this is simply an equation in one dimension. Our numerical code would work in 3 dimensions. It was actually a 3-dimensional spring. Here I really have a 1-dimensional situation, so that may be just fine. The other thing I'm leaving out of this discussion is I haven't put gravity in. I could add gravity onto this as a force. This would just have a plus g. I have an acceleration over here. I have a plus g over here. And what it would change is the equilibrium solution to the problem. But I'm not going to do that right now. So we're just going to solve this. So, all right. Looking at this equation, one of the most standard ways of solving a differential equation is simply to guess the solution. It doesn't sound fair. It sounds like it's cheating, actually, but it's a very important technique. Differential equations can be so hard to actually solve in any other way that if you can guess a solution, by all means, go ahead and do it. And we can, in fact, by inspection, guess a solution to this right away. The first one I'm going to guess is that x of t equals L0. It's a trivial solution. It means place the mass at its equilibrium position and just let it go. And it just sits there. So if we put x equals L0 into this side of the equation, I get 0 over here. If I take the derivative of a constant, I get 0 over here. So I get 0 equals 0. It's absolutely a solution. So this is called an inhomogeneous solution or a particular solution. It is one solution to the inhomogeneous equation. Since we have that, we can actually go on to find a bit more interesting solutions by just looking at the homogeneous problem, getting rid of that constant. So our new problem now is going to be a second order equation, but doesn't have the constant onto it. We already have a solution for that, the trivial one. X of t just equals a constant L0. All right, what does this equation say? It says I want to take two derivatives of a function and get back the same function with a constant proportionality. Now, we have a couple different things we could try to go there, but the one I'm going to use actually is the exponential. I know that if I take the derivative of an exponential, I get back the same function. And if I take the derivative again, I'm going to get back the same function. And I get a constant out in front of it by having a factor in the exponent, alpha t. So I'm going to guess that the solution is some form that says x of t equals some constant times e to the alpha t. All right? Now, let me just rewrite that equation as the second derivative of x with respect to time plus a constant times x of t equals 0. And I'm going to substitute in my trial exponent. All right? When I take two derivatives of that, I'm going to get alpha squared. When I just multiply by x of t, I'm going to get a k over m times that value. But I'm going to be able to divide by a e to the alpha t out of that, and I get what's called the secular equation. This is an equation that says that alpha squared plus k over m has to be equal to 0. And if this is satisfied, then this trial solution will work. This condition is satisfied when alpha is equal to the plus or minus square root of negative k over m. Okay? So if alpha is equal to either of these two values, then x of t is a solution. All right? Either value is equally good, a plus or a minus, so we don't get to pick between that. Now, there is something that's interesting about this solution, and that is that k is the spring constant and m is the mass. Both of those are positive definite quantities, and I'm now taking the square root of something which is a negative times those quantities, which means that in my exponent I have an imaginary number plus I times the square root of k over m, and a second solution minus I times the square root of k over m. Those are the two solutions that I find from my secular equation. I also have two arbitrary constants, a1 and a2. And so I have two solutions, one which is the positive complex exponential and one which is the negative complex exponential. Both of these are equally good, and so the general solution to these is the particular solution plus these two solutions, the homogeneous. So my general solution to the differential equation is an arbitrary constant a1 times e to the I, the square root of k over mt, another arbitrary constant e to the minus I, square root of k over mt, plus L0. These two constants are known, can be found by the initial conditions, such as the initial position and the initial velocity or initial momentum, will allow us to find what these are. So we solved the problem. However, the solution is not really what we expected. This complex exponentials could be the first time that you're ever dealing with them, and we're pretty sure that this mass actually bobs up and down in real space, not any sort of complex space. So for convenience, let me define omega being equal to the square root of k over m. All right, and this is going to be termed the angular frequency. I'll talk about it more later, but right now it just shortens up the notation. And so then my solutions look like e to the plus and minus I omega t. So whenever you have a function that you really don't know what it means, sometimes you need to expand it in a Taylor series. And so I'm going to expand this in a Taylor series around x equals 0 or t equals 0. And what we get is the first term, evaluating this function at t, and then they take the first derivative times t, second derivative over 2 factorial times omega t squared, out, carrying it all the way out. And it's an infinite series. Well, does this help us at all? It could. We have now half the terms which are real. That's great. Half the terms, however, are still have this I in front of it, are complex. Let's collect these terms so that I now have an infinite series which is real, and I have I times another infinite series which is real. This contains all even terms of omega t. Omega t squared, omega t to the fourth, omega t to the sixth. This contains only odd terms. Omega t cubed, omega t to the fifth, omega t to the seventh. You might say this is getting us nowhere. we have this complex exponential. We've broken it up into two infinite series, and we still have this I around. Well, we can write these infinite series in closed form, and you may not know this, but actually these are the Taylor series expansions for sine and cosine. So this is the sine function of omega t, and this is this is the cosine function, and this is I times the sine function for the argument omega t. And you should prove that for yourself by actually expanding out sine and cosine. And so here's a restatement of that. The cosine function only has even terms, starts out at 1, and has even terms of omega t. And the sine function is odd, starts with omega t and goes forward. And so what we've deduced is perhaps one of the most amazing relationships in mathematics. It says that e to the I omega t is equal to the cosine omega t plus I times the sine omega t. Richard Feynman, Nobel Prize winner, said that Euler's expression is our jewel and one of the most remarkable and astounding formulas in all of mathematics. It's really remarkable. I take the exponent of a complex amount and I get back my sine and cosine functions from trigonometry. Returning to the problem at hand, we've made progress. We've now returned to having cosine and sine functions instead of a complex exponential, but we still have a complex expression. There's still an I in this. But one of the things we need to remember is that we had two solutions. We had e to the I omega t and e to the minus I omega t. Now, e to the minus I omega t is equal to the cosine omega t minus I sine omega t. That's because cosine is an even function and sine is an odd function, so in the odd function the minus sign comes out front. Now, by adding these two together and dividing by 2, we can find the cosine of omega is equal to e to the I omega t plus e to the minus omega t over 2. Now, we're allowed to add and subtract solutions together. We had a linear combination of a1 and a2 that we were allowed to use, so we could combine two solutions and get this. Likewise, we can subtract two solutions to yield the sign. So e to the I omega t minus e to the minus I omega t divided by 2I is going to be equal to the sign. So what that means is we can change from a form of a solution which involves a complex exponential to form which involves real trigonometric functions. So we have a new form of our solution, which is an arbitrary constant a times the cosine of the square root of k over m t plus a second arbitrary constant b times the sine square root of k over mt plus our inhomogeneous solution L0 that sets more or less where the equilibrium length of the spring is. So it turns out that often it is more convenient to use a form of this expression which uses a single trigonometric function with some new arbitrary constant which is determined by initial conditions, c times the sine of the same square root of k over mt plus now a phase factor. So these are equivalent expressions, and many times students have trouble seeing how I can add a cosine function which has one amplitude and a sine function which has a second amplitude and get a single harmonic function which has a new amplitude but a different phase factor. So I created a couple Python programs which will show you that. I wanted to spend a moment discussing how you can add a cosine function of length A and a sine function of length B together and get a single trigonometric function with a new length and a different phase angle. Some students find this hard to understand how you can do that. So I wrote a couple programs to let you visualize that. In this program we have a vector to represent A cosine omega t and a second vector b sine omega t. So they're represented by vectors of length a and b rotating at a rate given by omega. So the phase angle is omega t. That's why the two vectors are parallel. They both have an argument equal to omega t. The red ball is showing the cosine of omega t, and the yellow ball is showing the sine of omega t times b. So we have our a cosine omega t being the red and b sine omega t being the yellow. Down below you'll see we have the sine function in yellow, that's the b, and you have the cosine function in red, that's our a, and then when you add these two together you get the white dots. So you get a new harmonic function, which is neither a pure sine nor cosine. See, the peak is not peaking at the origin, it's not crossing zero, so it can't be a sine or a cosine function, but it's a new harmonic function. And so we can represent these vectors a little differently to see how that vector addition comes. It's actually hard to add a cosine function plus a sine function. It's easier to add two trigonometric functions which are the same. And so what I'm going to do in the next simulation is I'm going to take this red vector and I'm going to shift it by 90 degrees. I'm going to add 90 degrees to omega t. And then instead of looking at the cosine, I'm going to look at the sine of that angle, because you know that the cosine of theta is equal to the sine of theta plus pi over 2. So let's run that new program. And here what you see are vector A leading vector B by 90 degrees. They're both rotating around at a rate given by omega. And you can see their projections onto the y-axis, or the sine value of the two, are being added together again to give you the white ball that's moving up and down. The white dots are the addition of the red and yellow ball. And the line, which is going through all the white dots, is a tracing out of the sine of this white vector, the vector addition of A and B. So we have a new vector which is exactly reproducing the component addition of vectors A and B. So this new vector has a different length than A and B, but it's easy to figure out what that length is because it's just the addition, the vector addition of A plus B. And so this length is equal to A squared plus B squared square root. How do we find the angle, the phase angle? Well, this angle is given by the arctangent of B over A, but that's not really the angle we want. What we want is this interior angle, because we know that B has progressed by an amount omega t, and we want to add to it this angle. Well, this angle, by opposite interior angles, is this angle, or the complement angle, and that's equal to the arctangent of A over B. So this vector is a new vector which has length A squared plus B squared square root and has phase angle omega t plus the arctangent of A over B. And that's just what we produced in your notes. Right here. So the relationship between the amplitude of the new harmonic function C is just given by the Pythagorean theorem, and then the phase angle is the inverse tangent of A over B. Now that you've seen how we can combine these two functions together to get a single trigonometric function, let's go about examining the argument of this function. Our solution is x of t equals our constant c times the sine of omega square root of k over m we define as omega t plus the phase. So this is called the phase factor. This is the initial phase. When t equals 0, the argument is equal to phi, and sets where the vector starts. So you can represent this solution as a vector of length c, rotating around with a rate omega, starting at some initial phase given by phi. The time it takes to move around is given by the square root of k over mt being equal to 2 pi. Every time this argument changes by 2 pi, the vector will have made a complete circle. Your sine projection would have made a complete oscillation. So one period, capital T, is defined by omega t being equal to 2 pi. Or t, the period, is equal to 2 pi the square root of m over k. If we want to know the frequency of oscillation, that's just 1 over the period. This is the number of cycles per second. That is 1 over 2 pi times the square root of k over m. And if instead of wanting to know cycles per second, you wanted to know radians per second, or the angular frequency, you would multiply this by 2 pi. And then we would get that the angular frequency omega is equal to 2 pi times the frequency, or the square root of k over m. So imagining this as a vector of length c rotating around at rate given by omega, And your displacement, x of t, is given by the projection onto the y-axis, or the sine of this angle times c, is one way of visualizing that. And I thought I would show you, here is it for a particular example when c equals 1, omega equals 1, and the phase is equal to 3/4 pi. This was generated by a computer program, and I have a rotating vector and the projection onto the y-axis, and you'll simply see this oscillating up and down and the trace that it gives, and then I've included the code for that. So I'd like to visually show you the close connection between circular motion and simple harmonic motion. So I've written a Python code which produces a vector that rotates with a constant angular frequency omega. You'll be able to look at the tip of the vector rotating in circular motion and its projection on the y-axis, or the sine of the position of the vector. If we run this code, we see a vector which is rotating around in circular motion, and the projection on the y-axis which is oscillating up and down. And if we graph that position of the red ball, the position of the tip of the arrow, as a function of time, we get a sinusoidal function. Now, this is neither sine nor cosine. It actually looks like minus sine. We've started with an initial phase angle of pi. So we've rotated our vector initially to start out in this direction. So initially it started at 0, but it went into negative values first. So that can be changed by the phase angle. So let's put the phase angle to 0 and see what happens. The vector lies along the x-axis, and we generate our sine function. If I change that then to rotating by pi over 2, I'll now have my cosine function. If I use some value in between, I'll have something that's neither sine nor cosine. See, we're not at a maximum at time equals 0, nor at a zero crossing. It can't be a sine or a cosine function. This is controlled by the initial conditions of the problem. So if you took a mass and you were to move it away from equilibrium and release it, then you will have started at a maximum displacement. And so that would be a cosine function. If, on the other hand, you took it and started at the equilibrium position but gave it a push, then you'd be starting off with a sine function. You have the equilibrium position, but yet have some initial velocity. Or, of course, you could displace it and give it a push, and then you would have this mix condition. So the phase angle is determined by the various conditions of starting the mass oscillating, as is the amplitude.